lecture, we have discussed the Hahn Banach theorem, that is the linear functional extension of for the linear functional in case of a real vector space. That is, if X be a vector space and Z be a vector subspace of this, and F is a linear functional defined over Z, and P be a sublinear functional over X defined at each point on X, and F is a linear functional which is dominated by Px for X belonging to Z, then Hahn Banach theorem says that this linear functional can be extended to a linear entire class X, a linear function f delta, such that f delta x is also linear and dominated by p x for every x belongs to capital A. So, this is what we have the Hahn Banach theorem in case of real vector space. Okay. Sublinear functional we mean a functional which is subadditive. Sublinear functional means a real valued function p on a vector space, real valued functional p on the vector space X, which satisfied the condition of condition that it is subadditive and positive homogeneous, that is, this is equal to p of alpha x is alpha of p x when alpha is greater than or equal to 0 for all alpha in R and x belongs to. So, this is sublinear function. It means in case of the Hahn Banach theorem, we can extend a linear functional from a vector subspace to the entire class to a bigger vector space X, retaining the same property of linearity and majorization. Now, today we will discuss a generalized form of the Hahn Banach theorem. We should not restrict only for the real vector space. Even if a vector space X is a complex valued vector space, still the extension of the linear functional on the entire class is possible, retaining the properties of the functional f on Z, whatever this is. So, we get the Hahn Banach theorem in a generalized form. This we call the Hahn Banach theorem, the generalized form, or you can say it is a general result for real or complex vector space. Okay. Let X be a real or complex vector space and P a real valued functional on X, which is subadditive subadditive, that is additive TIVE, okay, subadditive, that is P of x plus y is less than equal to P x plus P y for all x comma y belongs to capital X, okay, and for every scalar alpha, this may be real or complex, because we are taking a complex vector valued vector space, satisfies P of alpha x is mod of alpha into Px, okay, Px again x belongs to, okay. Furthermore, well, the x is element of capital X. Now further, more, let f be a linear functional which is defined on a subspace Z of X. X is a vector space satisfying and satisfies condition mod of f x is less than equal to p x. Mod of f x is less than equal to p x for all x belonging to Z. Okay. Then this generalized form of the Hahn Banach theorem says that the f can be, then f has a linear extension f delta from Z to entire x, satisfying the criteria condition f delta x mod of this is less than equal to p x for all x belonging to capital X. Okay. Now let it be for our purpose, let it be this equation p x plus y, let it be denoted by 1. When the proof we will mention the equations, okay, let it be this 2 and this part is 3 and this condition let it be 3 star. Okay. So we prove this, any particular case it comes as a real. Okay. So proof. So let us prove first this for the real vector space, because under the real vector space this condition remains hold good or not. Okay. So real vector space, for this real vector space, let us see first. Suppose f is real, if x is real, thus then 3 implies that f x will be less than equal to p x, because f is real. So either it will have positive value or negative value, but absolute value is less than x. So f x will be less than equal to p x for all x belonging to Z. Okay. Now p is a sublinear functional, because when you take alpha to be positive, mod alpha is replaced by alpha, it is subadditive, positive homogeneity, x is real and f is a linear functional satisfying dominated or measured by p x. So we can apply the Hahn Banach theorem in case of the real vector space. So by Hahn Banach theorem, so by Hahn Banach theorem for the real vector space. This f can be extended to the entire class capital X, retaining the same property of f delta x is less than or equal to p x. Okay. So, by Hahn Banach theorem, there is a linear extension f delta from z to x such that f delta x is measured by p x for all x belonging to capital X. Okay. So, this part is clear. Now, to show that this mod f delta x is less than p x, we take this now minus sign. So, now consider to establish the 3, to establish 3 star, what we do is, let us consider minus of f delta x. F delta is a linear extension because of this Hahn Banach theorem. So, minus sign will come inside and we get f delta of minus a. But f delta x is less than or equal to p x for all x. So, this is less than or equal to p of minus x. P satisfy the condition of the homogeneity, that mod of alpha is p x. This is this condition, p alpha x is mod alpha p x. So, we get from here is minus 1 mod of this p x, which is equal to p x. So, what we see here is that f delta x is less than p x minus f delta x is also less than p x. Therefore, it will imply mod of f delta x is less than or equal to p x for all x belonging to capital X, and this completes the proof for in case of the real vector space. Clear? Now, let us come to the second part, where it is a for a complex vector space, for complex vector space. Okay. So, let us take the x to be a complex vector space. Let x be a suppose x is a complex vector, then z, which is a subspace of x, will also be a complex vector space, will be, then z is also will be a complex vector space, or then z is also a complex, or you can choose z is a complex vector, will be all is, that is better, is a complex. Okay. It can be real, but we are taking this complex. Okay. Okay. Hence, f is a complex. Now, functional f defined on S. Hence, because z is a complex vector space, so functional, when we are defining linear functional, it requires the alpha, beta and all these things, and we assume that f is also a complex value. Then f is complex valued linear functional. Okay. Complex valued linear functional defined on z, defined on z. Okay. So, we can write it f x as the real part and imaginary part of f, that is f 1 x plus I times f 2 x, where f 1 and f 2 are the real and imaginary are where f 1 f 2 are real imaginary part of f, but f 1 and f 2 both are real valued function, real valued function. Okay. So, this one. Now, we wanted to show this linear, this linear functional, which is a complex valued linear functional, can be extended to the entire class X, f delta X, and satisfying the conditions of 3 star. So, what we do is we first look the behavior of f1 and f2. Okay. So, for this, let us assume for the time being that for the moment that z and x which are taken to a complex value, let it be a real value. Okay. So, for a moment we regard x and z as real vector spaces and denote them by xr, r is real, and zr, okay, respectively. What do you mean by this? It means we are allowing the scalar to run through the real only. That is, the meaning is that is we are restricting, or we restrict multiplication by scalars to real numbers only instead of complex number. Complex numbers. Okay. Now, since f is linear on z, since f is linear on z, f1 and f2 are real valued function, are real valued defined on z, are real valued functional, real valued and linear functionals defined on zr. And further f1x is less than equal to mod of fx. f1x is less than equal to mod fx, because fx has a real part f1 and remaining. So, f1 it will always be less than, real part will always be less than or equal to its absolute value, absolute its modulus value, mod of fx. So, real part is less than equal to fx, hence by 3 replace this by mod fx by f1x. So, by 3 we get that f1x is less than equal to px, f1x is less than equal to p for all x belonging to z. Now, f1 is a linear functional defined on f1x belongs to r, zr, sorry, this zr. f1 is linear on zr, f1 is dominated by px on zr. So, by Hahn Banach theorem, it has an extension, linear extension f1 delta defined on the entire class xr. So, Hahn Banach theorem, there is a linear extension f1 delta of f1 f1 delta of f1 from zr to xr, such that this f1 r f1 star x is dominated by Px for all x belonging to XR, all x belonging to XR. Okay. So, the real part of the F1 satisfied the condition of this on a real vector space XR, on a part of this. Okay. So, let us take the F1. Now, once F1 is there, let us take the x2. Okay. Now, we turn to F2 now. So, what we do is returning to Zn. So, return Z and x, means now you take x as an element of Z or as an element of y, and f, which is the F1 plus I F2, is linear on Z. This is linear on Z. So, okay. So, for every x belonging to Z, I times of f x, this is equal to basically I times of f1 x plus I times of f2 x. But f is linear, so this will be equal to f of I x. Again, f of x is this, so we can write f1 of I x plus I times of f2 of I x. Is it not? Therefore, if we equate the real and equating the real and imaginary part, what we get from here is the f2 x, the real part of this is minus f1 I x. Is it not? So, f1 we have got it, f2 also we get it in terms of f1. Hence, for all x, hence if for all x belonging to x, let us set the functional f delta x as f1 delta x minus I times of f1 delta I x. Okay. Now, if I set this f star x when x belongs to capital, then clearly if x is restricted to z, x is restricted to z, that is if x belongs to z, then this f delta x, let us give the number here again. Okay. So, this is 5, we have seen up to here 4, what was the 4 here, third star we have gone, is it not? So, what is the fourth is, the fourth one was f delta x is, yeah, this is be fourth, let it be this fourth. Okay. And then we are taking to be the fifth and sixth as fifth, we can take to be, this is fifth. Okay. Let it be fifth. Okay. And then let it be sixth is f2 x, and this one is 7. Okay. Let us mark this thing. Now, we use. Okay. So, what we say, if x is restricted to z, that is if I take x, then sixth we can see that f2 x is nothing but minus f1 I x, that is f star x is f x on z. So, then 6 will give, because f2 x is minus f I x and here is f1 x is also there. So, f x this part, f x which is equal to f1 plus I2 f2, I2 x means I1 f1. So, here we can write f2 in place of this. So, whenever the x in z, then we can say that f is delta x, f delta x equal to f x on z, is it not? Because the f x we are introducing in this fashion, this is our f x, and when f2 is replaced by this number, then basically this 7th and reduced to this part, and we get x belongs to z, then f delta x equal to f x. Now, we have defined the f delta x to be this for the entire x, and for this one we are getting this as f1 x, okay, and then minus I times of f1 of I x, clear, I x. It means if I take the extension of this, f2 is minus f, so the extension of this on entire x is this one, clear. So, this clearly shows, this shows that f delta is an extension of f from z to entire x. Okay. Now, if I prove that f delta is a linear, then and f delta is linear and satisfy the condition of 3 star rate dominated by p x, then our result is proved. Okay. So, now it remain to show that number 1, f delta is linear functional on the complex vector space X. And the second part is left is that f delta satisfies 3 star on X. Okay. So, if I prove these two things, then our result is complete, the proof is complete. So, proof of first part. In order to prove this thing, let us consider, okay, let us consider this expression f delta of a plus I b x. Take any f delta alpha x. If I prove alpha times f delta x, then f delta becomes linear, is it not? Because addition is also satisfied, f delta a plus b equal to f delta a, which can be shown quickly. So, it is only proved the linearity of this vector space, hence a plus b. Okay. So, now by definition this is the f1 delta a x plus I times b x, and then minus I times f1 delta I x. So, I f a x minus of b x. Okay. f1 star delta is a linear extension which already have proved. So, this can be written as a f1 delta x plus b f1 delta I x, then minus I a f1 delta I x minus b f1 delta x, and then combine this thing, we are getting a plus I b f x. That just we can write it f1 I a and so on. So, this shows that f delta is linear. To prove the second one, so f delta is linear. Okay. Because f delta is defined here is. Now, to prove this thing third, that is required to show is required to prove that mod of f delta x is less than equal to p x for all x belonging to x. Now, if suppose f delta is 0, f delta x is 0, then for any x as such that then third holds, because p x will always be greater than equal to 0, because p x plus y, because p x plus y is less than equal to p x plus p y, and p of alpha x is equal to mod alpha into p x. Okay. So, if I take here x y is 0, x is 0, then we get from here these two implies p of x will always be greater than equal to 0. Okay. This is y. Let it y is 0. So, p x will be greater than equal to 0 always. Okay. So, we get from here. So, let us suppose let x be such that f delta x is not 0. Okay. If delta x is not 0. If it is not 0, then we can write its polar form. So, using the polar form, we can write f delta x as is modulus f delta x into argument e to the power I theta. Okay. Then from here we can say f delta x is equal to f delta x e to the power minus I theta. Okay. Now, e to the power minus I theta can be taken inside, and we get f delta of x e to the power minus I theta as f delta is linear. Okay. Now, since f modulus of f delta is real, therefore, the right hand side should also be real. So, the f delta x e to the power minus I theta is also real. Therefore, it implies that f delta x e to the power minus I theta should be its real part, should be equal to its real part, that is f 1 star of e to the power minus I theta x, its real part. But f 1 is already dominated by p. So, p of e to the power minus I theta x, therefore, this can be written as e to the power minus I theta p x, but this is 1. So, we get p. It means the modulus of f delta x, this is equal to what? F delta x, is it not? Its real part is this modulus of this. So, this shows modulus of f delta x is dominated by p x for every x belong. Hence, proved. Hence, theorem is proved. Okay. So, this completes the proof of this theorem. So, we have proved the Hahn Banach theorem in a general case also, when it is real or complex vector space, all complex. Now, if x be a norm vector space, norm linear space, then also can be apply the Hahn Banach theorem. Though it does not say anything about the continuity of the functional, it simply says the f is a linear functional which can be extended from a subspace to the higher to the entire vector space x. But even if the functional f is a continuous linear functional, that is a bounded linear functional, okay, then also one can extend this bounded linear functional from a norm subspace to the entire norm space x. Okay. And this will give you further the generalized form of the Hahn Banach theorem in case of the norm space. Okay. So, let us see the other also norm is Hahn Banach theorem, other form of the Hahn Banach theorem. In case of norm spaces, let f be a bounded f bounded linear functional on a subspace Z of a norm space X. Then there exists a bounded linear functional f delta on the entire space X, on the entire norm space X, which is an extension of f to X and has the same norm as the norm of f on Z, has the same norm, that is norm of f over the entire X, sorry, norm of f delta X, norm of f delta over the entire X will be the same as the norm of f on Z. Where what do you mean by this norm f? Where norm of f delta X means, by definition, this is the supremum of modulus of f x, f delta x, where x belonging to capital X and norm of x is 1. Okay. This is by definition. And similarly, norm of f z means supremum of mod f z over x of f x, sorry, f x, when x belongs to z, this is x, and norm of x is 1. Okay. So, this gives the extension of the bounded linear functional to a entire norm space, from subspace of norm to a entire space. The proof of this theorem is easy. What we do is, we try to develop a sublinear functional P in terms of the norm of f over z, and then once it is a sublinear function established and f is dominated by the sublinear functional, f is linear on z, then by using the Hahn Banach theorem for real vector space case, one can get the result quickly. Okay. Now, let it be this number be 8. Okay. So, if suppose if z is a singleton set 0, that is a norm subspace containing only 0, then obviously the linear functional will be only f will be 0 and its extension, and hence its extension is f delta, which is also 0 on x. So, it is nothing to prove much. Now, if z is different from singleton set 0, now we wanted to make use of the Hahn Banach theorem for the real vector spaces. So, what we do is, let us consider a pseudo. So, for all x belonging to z, we have mod of f x is by definition modulus, f is a bounded linear function. So, modulus of f x is less than or equal to norm of f into norm of x, and the norm f is taken over z because x is point in z. So, the right hand side is, we can choose p x as norm of f z into norm of x, because it is a real valued functional, it is a real valued. Now, if P is also subadditive and positive homogeneity, then it will satisfy the. Clearly, P is sublinear. P is sublinear functional. Why it is sublinear functional? Because if we take this thing sublinear functional for entire x, for over for all x, sublinear functional over entire x, x norm. Why? Why it is sublinear functional over entire norm? Because P of x plus y, we can write it as norm of f z into norm of x plus y. Okay? Norm of x plus y, because norm is taken to be the same. Now, this is norm space, so it is less than equal to norm of f z into norm of x by triangular inequality, norm of z into norm of y, and this gives the p x plus p y. Similarly, p of alpha x, when x belongs to, remember on x, okay, then this is equal to norm of f z, norm of alpha x, then this will be equal to mod alpha into p x when x belongs to capital X. So, p is a sublinear functional on this, and our f is dominated by the sublinear functional p. So, by using the, so use Hahn Banach theorem for real vector space. Okay. So, what we conclude is there exists a linear function f delta. So, there exists a linear, there exists an extension, or we conclude that there exists a linear functional f delta on x, which is an extension of f and satisfies the condition mod of f delta x, which is less than equal to p x, which is basically equal to norm of f z into norm of x. Okay? Norm of f z into norm of x. Now, divide by x. So, we get from here is f delta x over norm x, take the supremum over all x belonging to capital X, where norm of x, supremum over x over the norm x is equal to 1. We get this is less than equal to norm of f z, but this one is nothing but norm of f delta, which is equal to, so this implies norm of f delta over x is less than equal to norm of f z. Okay? Clear? But z is a vector subspace of x. Sorry, norm subspace means it is a vector subspace of x. So, norm of f delta x cannot be lower than the norm of f over z. Okay? That is because it is extended. Therefore, combine these two, we get norm of f delta x equal to norm of f z, and that proves the result. Okay? That proves the theorem. Okay? Now, clear? So, we have seen the vector space, we have seen the case in the norm space. Now, in Hilbert space the situation is very simple. So, remark, okay, in case of the Hilbert space, that is a subspace of Hilbert space, this can be obtained with the help of the Riesch representation theorem. So, let us take if Z is a closed subspace of a Hilbert space X, which is say equal to H. We are denoting Hilbert space by H. Then F has a Riesch representation, then every bounded linear functional F has a Riesch representation. This we have already discussed. That is, every bounded linear functional, that is f x, can be expressed in terms of the inner product x z, where z is uniquely determined by f, z is uniquely determined by f and norm of z equal to norm of f. This is by Riesch representation theorem. Okay, since this inner product is defined over the entire H, so this gives the, since the inner product is defined on all of H, so this gives on all of H. So, this gives at once a linear extension of delta of f delta of f from Z to S, and f delta has the same norm as f, because norm of f delta is also norm of Z, and norm of Z is norm of f is already proved with the help of the Riesch representation theorem. So, this completes the proof. Okay. So, we can go for the Hilbert space also. Now, as a consequence of this, one can find out one Hahn Banach theorem gives the guarantee that a norm space is enriched by a boundary linear function. That is, we have sufficient number of the boundary linear functional defined on the norm space, so that the theory of the dual space can go very smooth. And in fact, a result will tell you that if we pick up an element x in a norm space x, then corresponding to this we can always find a boundary linear functional satisfying the Thurston criteria, and that result is a very interesting one. So, we form a result in the form of theorem, that is the bounded linear function. We also bounded linear. This result is for bounded linear functions, okay, on the norm space. Let x be a norm space and let x naught is not equal to 0. We any element of x, then there exists a non-linear functional f delta on x such that norm of f delta is 1 and the value of f delta at x naught will give you the value norm of x naught. So, what this shows? This shows that if x be a norm space and if we picked up any non-zero element vector in x, then there will always a boundary linear functional associated with this x naught, which has this property that norm f delta is 1 and so the norm space are very much enriched with the boundary linear functional. That is what is okay. The proof is to prove this. Let us consider a subspace. Now, x naught is that our x naught is our point in Z. X naught is a point in X. Okay. Let us consider a subspace Z of X. Consider a subspace Z of X consisting of all elements x which is of the form alpha x naught, where alpha is a scalar. Okay. Now, so this form is subspace, clear, because it is generated by R. Now, on Z define a linear functional f y f of x as x means alpha x naught as alpha times norm x naught. Okay. Then obviously f is bounded because the mod of f x is less than bounded, mod of f x is and has the norm 1. Why? Because what is the mod of f x? Mod of f x means this mod of alpha x naught, okay, but alpha x naught is mod alpha into norm of x naught, which is equal to norm of x, because this can be written as okay, norm. So, divide by this. So, we get f x over norm x. Supremum of this is less than equal to 1, which is the norm of f, but norm of f we can choose the point x equal to x naught, but norm of f is greater than equal to f x naught over norm x naught, and that is equal to 1. So, this shows norm f is equal to 1. So, it has a norm. Therefore, so by previous theorem for Hahn Banach theorem, in case of norm space, if we apply this theorem, then this implies that f delta f has a linear extension is a or f has a linear extension f delta from Z to x of norm same as norm of f, okay, which is 1. And this, if I put it again, therefore, what is the end? What is the norm of f x, norm of x naught? If I take this f delta x naught, then f delta x naught will be equal to f x naught, which is equal to norm of x naught, and this proves the result. Okay. Thank you. Thanks. So, this